Okay, so we're starting a new chapter, and the chapter is about something called a radial basis function, or Rbf. And so this is a nice way of introducing a neural network. So this is going to be an example of a we can call it a feed-forward neural net, but it's just a normal neural network. And the nice thing about this neural network is there's kind of a nonlinear piece, and then there's a linear piece. And so we can use our linear algebra to solve the linear piece. Okay, and so one thing about this neural network is it's an example of something called a universal function approximator. And that's a really big deal. It's this property about that there's for if you give any, so let me just maybe I should write it down. I was just going to talk and wave my hands, but you can't see me. Given an arbitrary function from Rn to Rm, and we should say this function has to have some nice properties. This isn't going to be true for just any kind of weird function. Continuity would be nice, for example. Differentiability. So the function can't be too bad. So I should be careful about the arbitrariness of my function here, but we'll ignore that for the moment. So given a nice function from Rn to Rm, we can find an Rbf that will approximate it with any given error tolerance. Okay, and so that means that if I have some data set, right, that I want to find a function for, then I can find an Rbf that will it will approximate the function to an arbitrary degree of fineness. And so and I even have to be careful with that because we're assuming, right, that we have enough data that actually defines the underlying function, and so that can be a bit of a misnomer as well as okay, anyway. I don't want to get too buried into the theory, but I will say that these using an Rbf as a neural network really started with a guy that's a really good mathematician, or he was unfortunately he passed away several years ago, but I worked with him a few times with my advisor over at Colorado State, David Broomhead. Really good mathematician at the University of Manchester when I knew him. And he worked with David Lowe on the paper that brought the Rbfs into the neural network audience. And this was being done in 1988. And so it's pretty early. I should say a guy by the name of Powell was doing this Rbf's work in the late 70s. And he was doing interpolation, though, instead of regression. And so just as a reminder, when we talk about interpolation, right, that means we have some data and we want our function to go exactly through that data. Okay, in regression, which is typically what we're doing with neural networks, is we have some data and we're trying to find like some kind of best fitting curve. Okay, and so interpolation is exact, and regression we have error. Okay, so you would do interpolation in things like computer-aided drafting when you need you need your functions to be perfect. Regression functions, though, you're assuming that there's some noise going on, and so you're trying to just find some kind of best fitting function. Alright, so we're going to see that an RBF, radial basis function, can be used for both interpolation and regression, but we're going to be using it for mostly regression. Okay, so how does an RBF work? RBF action. So if I have a vector x, I'm going to feed it into I'm going to draw some cells here in just a second, but let me talk about, maybe before I talk about the action of the RBF, I'll say Rbf Model Parameters first. So what defines an RBF? As it turns out, an RBF is defined by two things: centers and weights and biases. I guess that's three things. Oh, you know what? Let me save the weights and biases for later, because if I have the centers and the transfer function, then I get the weights and biases, W and B, from linear algebra. And so that's really defined just by the centers and the transfer function. And then the weights and biases will come for free. Okay, so the centers are in the same space as the data. So I'm thinking about either like classification or regression, where you have a domain. So this is in the domain. Okay, and we have k centers. And so what we're going to do is I'm going to take a vector x that's in Rn, and then I'm going to take the distance from x to the first center, and then the distance from x to the second center, and so on down to the kth center. And notice that this is now a vector in R K. Good. And now what I'm going to do with this is I'm going to apply phi to each of these elements. And phi is called the transfer function. So phi is going to be applied to these vectors, or to this vector. And what I mean by that is it's applied element-wise, right? And now, what am I going to do with this vector in Rk? I'm going to take W times that. So this is like my x, Wx plus b. And this is going to be the output. So somehow I ran out of space for that. Let me rewrite this. In fact, let me pause and rewrite it. Okay, let me take another stab at this. Okay, so we start with a vector x in Rn. And so we think of this as having n nodes in this first layer. And what happens is we're going to connect these up. I'm going to think of this as having k cells. Okay, and at each cell what happens is I'm taking in my input vector x, right? This would be x1 down to xn. And then I'm going to compute the distance from x to c1 for the first cell, and the distance from x to ck in the last, right? And then I'm going to take the norm of that. And then I'm going to take phi of that. So we have to define what phi is, and we will do that momentarily. It's just a function from R to R. So it's just a real valued function. We'll talk about some popular options for phi. But the main point is that what comes out of this is a vector in Rk. And so I'm thinking of this as being like a two-step process, right? So the first step would be to construct this vector p in Rk, and this, I'm thinking of p as defining pre-state of the cell, and then the s is going to be the state of the cell. Okay, and so the state of the cell is going to be the phi of the norm of the x minus c. So the ith cell would be x minus ci. Okay, and then finally we take our vector that's in Rk and we map it to Rm, right? So that means we're doing an affine map here at the outset, and so, or at the output I should say. And so what's the size of the matrix W? Does everybody agree that it should be m by k? Because s is a vector in Rk, and then b is a vector in Rm, so that's going to be m by 1. And so, yeah, that's going to be our output. Good, and so we're going to do that for each data point, right? So each input I'm going to have a ws plus b for. Okay, and so then the training parameters then, once the centers are fixed and the phi is fixed, then we would find the w and the b. Okay, now maybe I should stop here before I go any further, so I don't have to stop in the middle of an example. Okay, so I will see you in the next video where we will talk about these parameters in this model.